run code examples in my slides.
See, Carson, his was automated. You had to do it yourself.
Next to the Go playground and runs them over a WebSocket. It's pretty great. I like it a lot.
I do something similar, but I had to do it manually with iframes.
Oh, I'm sorry. That sounds kind of not fun.
Yeah, I can actually show the tool.
So sub lesson of this was that you can use Markdown and automate your slide creation.
Yeah, Markdown. Yeah, the present library by the Go maintainers are it's great.
Anthony, when you give your talk at the St. George meetup, I expect you to use Markdown.
Okay.
Those slides.
All the cool kids do their presentation with Markdown.
I don't know when you'll ever do that, but
Annoying. I was going to do
There's expectation.
Man, this is much nicer for code examples. Yeah, code examples. So, my name is Ryan Berger. I work for a company called Senior Woolley. It's out of Chicago. Probably haven't heard of it because you aren't high school students who are in a Spanish class. But we are kind of a game site. We build.
did you say a high school student in a Spanish class?
Yeah, I said you probably are a high school student in a Spanish class because that's what
Oh, that's what they do.
Right.
I thought you were trying to say that high school students work for this company because Spanish is boring.
No, I'm trying to say that only kids who are in high school and in a Spanish class use software where I work.
Is that because it's one who it's popular with? Because you'll be allowed to use it?
It's a teacher, so the teacher pays for a subscription for their class. So theoretically you could, but it's kind of built towards high school students and kids.
What's it called?
It's called Senior Woolley. I actually used it in high school, which is kind of weird. Anyways, I was asked to talk on concurrency and Go. I was expecting beginners. I think you all understand.
Olivia appreciates.
I'm new to Go, so.
Anthony appreciates.
I haven't done anything.
Okay.
I haven't done any concurrency.
Okay, cool.
You didn't like my explanation the other day?
What?
You didn't like my explanation of our coworker package the other day?
Oh, well, yes. I've had one lesson.
That's fake. I mean, keep going. We're waiting.
Cool.
We're waiting on you, Ryan.
Okay, so concurrency. So kind of what is it? Rob Pike put it really great. He does a talk on concurrency. I think it was at a GopherCon. I kind of took this graphic from it and this quote, but programming is the composition of independently executing processes. So lots of people will kind of tie the word concurrency to some sort of parallelization. They'll say I want to handle multiple requests concurrently, maybe when they're wanting to say the word parallel and kind of vice versa, and they kind of confuse it. But concurrency isn't necessarily parallel. So in this example, we have these gophers who are taking, I believe Rob said they were C++ books, and throwing them into a cart and then throwing them into the fire. So there's three independent processes here. There's the gopher who's putting things in the cart, there's a gopher who's taking the cart to the fire, and there's a gopher who is taking the books out of the cart and throwing it into the fire. That is all sequential, but that's concurrent, right? You're designing three different processes in order to kind of make a whole program. And then you can parallelize that if you want. And that's kind of not necessarily the goal of concurrency, but it's kind of a nicety of concurrency where you can make things parallel. So in this case, we have the gopher who is loading things into the cart, the gopher who's running the cart over, the gopher who's burning the books, and a gopher who is running the cart back. And the gopher running the cart to and back can run it at the same time, and therefore you can get higher throughput on burning your C++ books. So why is it really important? Well, web servers handle lots of requests at a time. That doesn't necessarily mean they're handling them in parallel, but they're handling them all at the same time. And the NetHTTP package already implements some form of concurrency for you, so you don't have to really deal with it. Computer peripherals are concurrent. Your mouse, your keyboard, you're kind of taking a bunch of input in at the same time. And you have different processes that are pulling in input, and then you kind of combine it into one thing, some sort of event loop. And then data pipelines is a real big one where maybe you have some user input data coming in, and then you're doing some machine learning and data processing on it, and then after that you have to store that result in the database. And you can kind of think of those as three separate processes, and you can then parallelize those processes, and so that you can get higher throughput. So there's a couple different concurrency patterns. I don't know if any of y'all have done like C# or JavaScript or Rust. However, they like this async await approach where you do a thing, you make a network request, and you wait for it to finish. And make network request is a function that is marked as async, which is just a keyword. And it goes off and it does its thing, and then it comes back and returns, some sort of value, and you can continue doing things. It's kind of a very synchronistic way of thinking, where you're going down each step, and you kind of think of it as if it weren't asynchronous at all. But the power of Go is that it doesn't necessarily give you that for free. So there's kind of two approaches to Go's concurrency. You have like a shared memory. Go routines, it's kind of one way that they deal with this. And Go routines, the functions that you are calling or you're creating the Go routine with can't have any return variables, whereas this await make network request could return, say, an int or something, or a struct. And you go off and you do your thing, it spins off a process, and it runs it on the Go routines. The Go routine scheduler picks it up and runs it. And you can continue doing things as if nothing really ever happened, and make network request is often doing its own thing. The other way to do it that is kind of really nice is communicating sequential processes. It's kind of a fancy term, but pretty much you can make kind of these pipelines or channels in Go where you feed work to it, and there's a separate process that's picking up work and doing work for you off to the side. So in this example, we just make a channel of ints. You can pass in work to it, and it will just print out whatever int you have plus 10. And then you can continue doing things. And that's kind of a nice way of doing things concurrently. So, okay. So I assume all of you have heard of race conditions, but maybe not race conditions. Okay, so which one prints first? Is my question to you guys. Let's vote.
Oh gosh.
So
Anthony, I'm voting with you.
does first print first or does second print first? Which one prints first in this? Do we have?
It's not.
What's first? Not deterministic is your answer.
I have to go with second.
Second.
It's not first.
Okay, second.
I'm going to go with the literal first prints the string first.
Okay,
I'm gonna go second.
second. And okay, let's run this boy. Let's see.
Wait,
Oh, but let's run it again.
I'm pretty sure that.
Yeah,
Oh,
right.
again, and it's
Nice.
weird.
It's not deterministic.
Undeterministic is the.
Because
That's a
of the,
race, right?
yeah.
It's meaning you can't guarantee A is going
Right.
to happen before B.
Right.
It's whoever happens to get into the processor.
Right. Yeah. So one of them gets into the one of them gets into the scheduler first, and then does its thing.
You don't know
yeah.
when it's gonna finish.
You
Like
don't
different
know.
times every
Yep.
time you vote.
And
Correct.
the big problem in programming when this happens is that first sets up something that second needs.
Right.
And it works and works until it doesn't, and the whole thing falls apart.
That's
Yes.
called a race condition.
Race condition.
That's really hard to comprehend.
And it's hard to fix. It's really hard to
I
fix.
still don't understand most race conditions.
That's
But
why.
it's okay.
That's why the Go compiler has the race option, and then it tells you exactly what's going on, which is really nice too.
It's still
That's a separate.
okay.
That's a separate thing. The race option is awesome. If you access data at the same time, it will freak out and panic. It's really great. Except it slows things down, so don't run it. Don't run it in production. Okay. Let's fix it with the shared. I call it the shared memory model because we're sharing memory between processes kind of in a global way. This isn't necessarily recommended, but anyway, so two processes sharing memory, right? The way that we do this is with the sync package. I'm using a wait group for this one. You can use, there's a ton of different things that you could use. The wait group pretty much says, tell us how many processes you're gonna run, and every time you finish a process, mark it as done, and then once all processes are done, the wait function will unblock. So In this case, we add 1 to the process, we start a process, and then we wait for the process to finish before we print second. So we're guaranteed here that first will always print first and second will always print second. So if we run it, we'll see first prints first, second prints second. And this is kind of one way of handling this race condition problem, because in concurrency, again, I said it's not parallel, and that's true, but sometimes concurrent processes access the same memory, and that can cause issues if you are to parallelize it. So the other way of doing this is the communicating sequential processes way.
Sorry, can I
yes.
ask a question on
Yeah,
that?
go ahead.
Go back.
So I don't know what a weight group is,
Yes.
but you have the add one.
Yes.
Is there a similar, like a subtract one?
The
Done.
done.
The
The
done,
done?
Done.
done
marks
automatically
it.
subtracts 1.
Yes.
Okay.
Yep.
So you can think of the number as a thread count.
I mean,
So it's adding threads, and then once that's completed, it's removed the go routine from that thread.
so does done subtract 1 or does it set it to 0?
Subtract 1.
Okay,
Subtract
so if you
1.
set it to 5, you'd have to say done.
Done 5 times, that's correct. So if you have like 1,000 go routines and you add 1,000, you have to wait for all of them to finish
Okay,
before.
cool.
Yeah,
Thank you.
yeah, yes.
To reinforce the relationship when I'm writing code, I like to start the go routine with a defer wait group dot done.
Oh, yeah, that's a good one. Go has a defer, which runs whatever function you say defer, and then you give it a function. It will run it at the end of a given function. You're saying in this case you would do like it in the main. You're saying like
You go right on
add
one line.
right above up at the top.
Yeah, I try to have the add and the done like 2 lines away from each other.
I see what you're saying. Okay, yeah. The defer is good too. I had a midterm when I wrote this code, so this was kind of like.
Yeah, no,
It's totally functional code.
This is
Yeah,
good educational code. It's more,
Yeah.
If you're trying to think through how it works, hard coding it is the best way to think through your process.
That's true.
Yeah.
Yeah.
If you ever want to understand defer, listen to Matt Ryder. He loves the defer function. He uses it.
It got a bad rap for a while because
Yeah.
it did cause performance issues, but that's completely gone now.
Yeah.
And even when it did cause performance issues, it was all pretty much, unless you're doing really highly performant things, it was fine.
Yeah.
it's so
They
worth
inline
it
it
just
now.
for readability.
Yes.
Yeah, for reliability, that I just did something that has to be undone. I put
Right.
them right next to each other.
Right.
Write your code for readability first, performance second, if at all.
Yeah.
Anyway, yeah, but that's still the best way to think through it is hard coding. So
Sure,
I
sure.
appreciate your code as
Thank you.
written.
Oh, thank you.
You get my vote of confidence, that means nothing.
Okay. Thank you very much for validation. I need it. Okay. So this example is a little more complicated, and I apologize. It's just kind of how it works. I'll explain. So the way that we're doing this, we're making some sort of work channel for things to print. It's kind of like a queue of things that we need to process. We create a finished channel, which I'll get to in a second. And we start up a process that says, listen for work, and as we have things to print them in the order that they came in. As the channel is a queue, right? It's taking things in, and it's pulling the work in the order that it has been put in. And if we run this, it's going to do the same thing, first and second, because we put in first and then we put in second. The whole finish thing is kind of complicated, but pretty much what happens is if you don't have it there, your go routine, the go func the program will exit and the go routine will still be running, and that's called a go routine leak. You don't really want those. Those can be problematic sometimes.
I would say 2 things about this. First of all, awesome that you're using empty structs for your channel signaling. That's very good practice. A lot of people will do like a Boolean or whatever.
Yeah.
Don't need that.
Yeah.
An empty struct takes no space in memory to go. So it costs you literally nothing.
Yeah.
And it tells the reader that this channel, I don't care the content of it, it doesn't matter. I'm purely using it for signals.
Yeah. And there's other ways of doing it.
That's
But
great.
that's the way I thought of doing it for this.
You probably should just close the channel, by the way, instead.
Yeah, I was going to say that was the other way I was thinking about it, was closing it. And I did this, I can't remember why.
You had a midterm.
I had a midterm. That's exactly what it was. I had a
You
midterm.
used empty structs, which makes me
Yeah.
happy.
Yeah,
Did you say you
infrastructure nice.
invented empty structs on your own?
Huh?
That's really well done then.
What, just empty?
Empty struct,
I didn't know that it was zero cost, but I did know that I really, hate like throwing a Boolean across the channel, and an empty struct does the job. So,
So,
and I think it's also in the Go programming book that I have. So I think maybe I picked it up from there, but that was just, yeah.
It's just convention, right? Right. I mean, a byte of memory doesn't actually matter on a program this big, right? But it's
Right.
good convention
Sure.
for just readability.
Yeah, absolutely. We only have one more slide. Okay, so the end goal of concurrency can possibly be parallelization. Doesn't necessarily mean that you want to parallelize things. So designing things in such a way that you have processes kind of makes it super easy to parallelize your program. So you can have a lot of workers doing some really hard work for you, and so that you are getting you're getting efficiency through throughput. It can be misunderstood though, because like parallelism doesn't necessarily mean that it's going to be faster. Lots of people like to try to do things that aren't necessarily parallel problems, and then they complain when they spin up 100 Go routines and it makes everything slower. And lots of times, solutions to problems can be done nicely concurrently. I know, like, I wrote like an HTML parser in Go, and there's this really nice concurrent way of like designing processes. So, you parse different parts of the HTML, and you're kind of handing it through a channel, and you're handing these tokens through a channel in order to kind of build out a new structure from whatever HTML you're going through. And that's a really nice way, but do I need to look through the document and have 5 workers that are sitting there like parsing through the document at the same time? No, I don't. But was it a really nice solution to the problem? Absolutely. And there's lots of other problems where you don't necessarily need things to be parallel, but designing concurrently and breaking up those processes into separate bits can create kind of a nice solution to your problem, I guess. But yeah, parallelism is very nice, and Go does that for you. Eventually, once you make enough Go routines, it decides that it needs a new thread. It will create a new thread for you and start putting things on the thread. And that's kind of a bunch of magic that I don't really want to get into. But yeah, Go really is built for concurrency, and it's really built for you to not have to think about these things, and you kind of design concurrently, and then you can you can parallelize it or not. But concurrency is a great way of thinking of processes and programming. So anyway, that's all I have. So thank you.